Good afternoon, everybody. So if you're here for the Energy 101 on microwave energy technologies, you're at the right place. Um, Today we're going to hear a little bit more about NETL's capabilities around microwave energy technology and any effects that may have, like groundbreaking research may have on the economic development and workforce development for the region and, of course, the nation as well too. Just as a reminder, we are recording this. The presentation itself will be available at some point on our website in our webinar archives, including the slides, and also on the NETL YouTube page. So just again, this is being recorded. So if you turn on your cameras, there's a good likelihood you'll be in the recording. So a little bit about some infrastructure. Everybody's on mute, just to help have a better presentation. Hear the presenters without any feedback. You may hear some feedback from me as they're cleaning the streets outside, so apologies for that. We're going to start off with learning a little bit more about the Regional Workforce Initiative from Anthony Armley, including some updates that we've had since the last one of these that we've had with you guys. And then we're going to move right into the Energy 101 discussion from subject matter expert and research scientist Christina Wildfire. And then we'll end today with a little brief Energy 101 Q&A session, talking about, again, some of the labor, economic development, and workforce impacts this type of research may have. And then again, finally, if you have any questions, use the chat function for those questions. So without further ado, we'll start off with our first speaker, Anthony. Anthony, are you ready?
Ready.
And just let me know when to go through the slides.
Okay, will do. Thanks, everyone, and welcome to our Energy 101 series webinar today. My name is Anthony Armley, Federal Coordinator for NETL's Regional Workforce Initiative. We started this workforce initiative in 2017 with an effort to promote STEM in the workplace, align future opportunities and technology to jobs that align to advanced manufacturing and energy, and to make this just to make a conscious effort, to do a better job with workforce in our region, and so that's what we've done. We continue to do that today. Next slide. Our mission is, we're looking to extend the mission of NETL's overall mission. We're trying to get technologies to market. We focus on this being a place-based initiative. We're focusing on the Appalachian region. We've created a wealth of stakeholders from many different sectors: academia, industry, non-governmental organizations, and really we've made a really strong effort the last 6 to 12 months on working closer with the other national labs. And I'll give some examples of how we've done that in the past year. Next slide, please. So when we started this initiative in 2017, these metrics, as you see on the screen, were zeroed out. Since then, we've grown them substantially. We put out a monthly e-note that if you're not subscribed, I recommend it. You can send me an email, or you can go to our webpage, which is netl.doe.gov/RWFI. In fact, I put the link to the webpage in the chat. If you scroll about halfway down, there's a button you can click to opt in. We have over 300 that subscribe to that. It contains a lot of valuable information, such as funding opportunities that are coming up, future workforce development opportunities, high-level newsworthy items that are coming out of our lab here at NETL. And we also, have a workforce projections section in there that we tend to put in. Our webinar series, we do a few different types of webinars, such as today, it's the Energy 101 series. We take a technical topic, introduce it at a very high level, so folks that may not have a science or technology background can better understand what we do at the lab, why it's important, how it impacts potential for jobs in the future, and then what skills might be needed to support said technology in the marketplace, in the workplace. Individual stakeholders from 0 to 800 plus under this regional workforce umbrella represented by over 400 different organizations. Next slide. So how do we grow our engagement? Is a couple different ways: consistent, meaningful engagement with folks like yourself. We do that by webinars, networking. We host a lot of visitors to the lab. If you have an interest in talking to me further about visiting us and learning more about what we do, send me an email. I'd be happy to host you or meet with you off-site. We put out the monthly e-note that I talked about. We archive all of our webinars, so we put them up on our page there. You can find it where it says Webinar Archives towards the top. Yeah, so just consistent, meaningful engagement has been our plan of attack, and it's worked very well. Next slide. So we feel like we're regional in focus. I mentioned the Appalachian region, but we have a strong national reach, represented by many different companies, universities, and other national labs. As I mentioned earlier. Next slide. Some successes that we've had in the past year, I'd say. We were recently selected for an award through IEDO. That's the Industrial Efficiency Decarbonization Office. We'll be partnering with the National Renewable Energy Lab and Oak Ridge National Lab. I'm not allowed to say a whole lot about that, but I did want to at least briefly mention it. We just completed a project, again, with NREL and a company called Julius Education, where we tried to project fossil energy skills and how those might overlap with the EERE, energy efficiency, renewable energy type skills that are needed for those types of jobs. We have a report that we're working on putting out for that. Another valuable collaboration that we've had in the past year is with the University of Pittsburgh. We help support their Applied Data-Driven Methods grad certificate program. We've partnered with them on a National Science Foundation grant application pending selection. And we did a partnership with them on a Justice 40 effort, measuring impact of the different metrics that our analysis team and their analysis team work on. And then lastly, I wanted to mention another national lab partnership is under the 2023 Office of Tech Transitions Technology Commercialization Fund. Brookhaven National Lab asked us to partner with them on a Minority Serving Institution Connect program. That's where you take potential students from minority serving institutions and align them up with technology IP from the various labs that are participating. It would be a 9-week summer internship where each student would get their travel paid for and would also get over a $10,000 stipend. They work virtually. The first week and the last week, they would be on site at the labs. The 7 weeks in between, they would work virtually with Zoom calls with the PI at the representing lab to answer questions and give feedback on the work that they're doing. So really excited about that project, which is expected to launch early 2024. I think it's going to be impactful, and I think it could lead to greater opportunities in the MSI in the MSI world in the future. Next slide. Just a quick slide here on, again, that University of Pittsburgh collaboration. I think it's been a great model that others could follow for how we could engage with NETL and RWFI. So the Advanced Data-Driven Methods program that they launched last year, it covers tuition for the students that are within the region and underemployed, whether it's because of COVID or energy transitions impact. Gives them an opportunity to have some skills that are highly in demand. Others that are eligible, unemployed, underemployed, and dislocated type workers, they're really trying to make it a regional effort, so they get preference. We help them out by providing awareness of this funding opportunity and other opportunities. We provided them with a letter of support on an ARC proposal, and then we collaborated with them on this ADDM certificate program. We are planning to potentially host a student fair at NETL upon completion. That'll help give them greater visibility to jobs, basically in the data analytics space. We also worked with them on a Justice 40 energy justice impacts measurement I talked about, weighting selection on the NSF grant proposal we put in, and then that career day for the students. So got a lot of good little things add up to a big impact, and proud of the work we've done with PID and continue to plan to do in the future with them. Next slide. So that's a quick update on the regional workforce initiative since we had one of these webinars last. If anybody has any questions, there's my phone number, my email. Link to our website is in the chat, as I mentioned, and happy to connect with you in the future. So thank you for your time, and I will pass it over to Christina, who will give you an update, an introduction on microwave technology at NETL. Thank you.
Thanks, Anthony. And Christina, whenever you're ready, you'll just let me know when to advance the slides.
All right. Hello, everyone. Thank you so much for attending today. My name is Christina Wildfire. I work here at NETL with the reaction engineering team, and I'm the champion for the Center of Microwave Chemistry here. And I'm going to give you kind of an overview of how we're using microwaves in industry and the trajectory we see in the future of industries that it'll impact, and also the types of careers available for this technology. So next slide. So you may be familiar, right, with our kitchen microwaves. We probably all use it on a daily basis, but what you may not know is that microwaves are used in a lot of different industries, from communication and navigation. It's used widely in manufacturing, and I'll give a lot of examples today, and then military applications. You may have seen news articles recently about microwaves being used to shoot down drones and things like that. So microwaves are popping up in a lot of different areas. Next slide. And so why microwaves? What's the deal with them? So microwaves live in between our visible spectrum light, sunlight, right, and radio frequency. You're familiar with radio frequency. It's been around a long time, and microwaves have also been around a long time, but I don't think are as understood, right, by the general public as some of these other forms of the electromagnetic spectrum. So we've been exposed to X-rays. We know the power of sunlight. So I'm going to explain a little bit why microwaves are just as powerful as some of these other tools. Click next. Yep. Again. All right. So the reason that we can use microwaves, especially in your home microwave, for example, when you're trying to heat up your food, the microwaves enter into the food. You have water molecules in the food, and that water molecule wants to ride along that wave. It wants to keep up, but it can't. And so it ends up just wiggling around, which creates frictional heat. And we're using that same principle to use microwaves in everyday chemistry. Next slide. So microwaves interact with, those water molecules by making it wiggle around and creating heat. But there's a lot of different other materials that we use in the chemical industry, especially things like catalysts, where we're trying to take, natural gas and transform it into other value-added products. So you have materials like metals, which are your conductors. You've always been told, don't stick something metal in a microwave. And there's a couple of reasons for that, right? So if you put a fork in your microwave, you can create arcing because you have a pointy metal object, and it creates like a little plasma on the end of it, which can be detrimental to your microwave. But if you put a big metal bowl in there with your food in it, your food's not going to heat because the microwaves can't pass through that metal bowl. You have insulators, which are your ceramic mugs, your plastic container. And when a microwave goes through that, it does nothing. It won't heat. So that's how you can put your plastic container or your coffee mug into the microwave, and it's heating the material inside of that bowl or cup. And then you have the interesting materials that I use every day, which are called dielectrics. And those are the materials that will absorb that microwave energy and heat up or do some other type of special effect. And we can utilize that for a lot of different industries. And the reason that's exciting, being able to work on a molecular level with the materials and heat in that way is you see on the right, when you're conventionally heating something up, like on your stovetop, you're heating the bottom of your pan. That pan is heating up and then eventually heats up the food inside. But with a microwave, we're not heating up the pan. We're heating up the material inside, and we're working with every molecule inside that pan. So everything heats up at the same time. So that cuts out a lot of processing time and saves us a lot of energy. So we've been doing this with food for 50 years. So why can't we do that in other areas? Next slide. So we wanted to apply some of these same appealing properties that microwaves have been giving us in our house for many, many years to other industries. So we wanted that same rapid heating, so that saves your processing time. It's a fully electric system. And so I'll talk about why that's really important to our future industry. We can have better economics, and we can have better economics at a smaller footprint. And that's something that has not been an avenue for a lot of like chemical production or just commodity production in general. Next slide. So when I talk about, being economic at a smaller scale, we're talking about manufacturing goods in a very different way. And so we can now make our commodity at the point of use. So all of our, manufacturing has been built on this economy of scale. We can make very big facilities, make a lot of products, and then we'll just distribute it. So that way you're only building one facility and we can optimize that for max production. But when we start thinking about integrating renewable energy, that isn't always the best avenue for producing our materials. Renewable energy can be intermittent. When we are looking at wind and solar energy, it's not constant. And when you make really large facilities, they need a constant stream of power. And if we want to capitalize on this renewable energy, we also have to have systems that can be nimble and respond to this renewable energy input. And so the microwaves are one avenue where we can fully electrify a process and load follow. We can use the energy as it's coming in and create these products. And then we can create these products closer to where they need to be used. So you can cut out a lot of transportation and storage of the things that you're making. Next slide. So I think we've seen a lot of good examples in recent history of why maybe this new type of thoughts in manufacturing are important. The current manufacturing relies on very large facilities. We have a very complicated supply chain. We're very global. And while that has been very good and is still a very good thing for us to be globally connected, when one canal gets blocked, we see the ripples and how long that ripple effect lasts because of this complex supply chain. And so we're also seeing a shift in the need to use unconventional feedstocks, waste feedstocks, really prioritizing a circular economy and being more sustainable. And so we're having to design these reactors and processes that go along with some of these waste feedstocks and provide local solutions, right? So the Midwest in the United States is going to have very different waste feedstocks than the East Coast. And so we need to be able to have systems that can adapt to whatever feedstocks that we want to put in them. Next slide. So along with just trying to shift the mindset of manufacturing, we're also seeing huge decarbonization initiatives within the DOE and industry, right? So everybody is trying to find ways, how do we cut our carbon footprint? We want to reduce our CO2 emissions. We want to make this renewable energy more affordable and more obtainable to a wide variety of industries. And so specifically, the DOE has put forth a lot of these energy earthshots to have these net zero carbon goals by 2050. So, in the next 30 years, we're going to have a lot of diverse solutions to bringing down hydrogen cost, to bringing down our CO2 emissions, and to electrify more of our processes. Next slide. So I want to give you one example of a chemical that is important to all of us, but probably a lot of us do not think about, and that is ammonia. And ammonia is used largely for our agriculture. It's used as a fertilizer, and it has fueled the growth of farming and food commodities around the globe. And so this is made in large centralized facilities. It requires very high temperatures and high pressures to reach its max efficiency, and it's been optimized for 100 years. It is at its peak optimal performance, but because of the size needed to make it economic, it results in these super facilities. There's 200 plants in the world that is, providing the entire world of its fertilizers. And as we look at projection and needs of agricultural growth, but also other growth in uses of ammonia, we're going to need a lot more of these facilities in the next 30 years. And these super facilities take a lot of money and 5 to 10 years to create a new facility. And then you have to secure the landmass, right, for these large facilities, and have large amounts of hydrogen input to go into making the ammonia. So if we try to reimagine what would be the needs to make ammonia more appealing and more approachable to more industries, and one would be rapid deployment. How can we take the time to create these facilities and significantly lower them by making these plants more modular? Can we reduce the processing conditions? If you have to stay high temperature, high pressure all the time, these facilities operate 24/7. It's very costly to bring them down and to do any sort of maintenance. And it takes many days to bring it back up to full operating conditions. So is there a way we can help mitigate that? And then we also need to be able to integrate with renewable energy. So that is, can we load follow? Can we produce ammonia when we have extra electrons and not produce ammonia when we do not have extra electricity? Next slide. So I mentioned this large growth in ammonia need over the next 20, 30 years. So it's mainly used for fertilizer today, but I know you have probably all heard of this upcoming hydrogen economy and our vision for a hydrogen economy of using this clean fuel to offset fossil fuels. One of the main barriers to using hydrogen as our main fuel is storage and transport of hydrogen. It's costly. It's not very easy to contain hydrogen, but you can contain hydrogen within ammonia. And ammonia is used globally. There's already storage and transport. There's safety structures around, the synthesis and storage of ammonia. And so it makes a lot of sense to use ammonia as a hydrogen storage chemical. And then it could feed into all of these other industries. But if we're going to use it for a hydrogen storage media, then we have to change the way that we make ammonia. Next slide. So we started a project about 6 years ago looking at, can we use microwaves to shrink the footprint? Can we bring down the pressures and temperatures needed? And can we make this a dynamic system? And we were able to, not only make the catalyst, but also the reactor and make it economic at scales that could service 95% of the farms in the US. It also has a lot of other small scale uses where the the companies are just storing a tank of ammonia, and they'd really like to have something that, you know, they can make the ammonia as they need to use it, so that they don't have it stored on site. It's a modular unit, so you have your base model that maybe makes 1 ton per day. If you need more capacity, then you can add reactors. And it's the same with, you know, integrating with the renewable energy. If you have extra energy that you need to store, you fire up 3 of those reactors, and then you can take it back down to 1 reactor when you don't have that excess amount of electricity. So we can think of, you know, dynamic loading of these reactors and scaling and making the plant integration very different than traditional plants are made today. And this is a fully electric green ammonia production when you pair it with renewable energy and electrolysis for hydrogen. So you can have your ammonia without a CO2 footprint. Next slide. So I mentioned, you know, that's one application in the chemical industry. But microwaves have been used in food and agriculture for quite a long time. And this is something more intuitive to us, right? Like, we use our kitchen microwave for food. So why shouldn't industry use microwaves for other, you know, food processing? And they do, and they have. And this is an industry that we point to a lot of times when we're trying to engage with, like, the chemical industry, to say, look, we can make microwaves at these larger scales. We can make them continuous processing. And the economics are already there for some of these applications. So you can do things like cooking the food, tempering, pasteurization, dehydrating food, extraction, and then roasting the beans that we need for our coffee every morning. And so companies are kind of moving towards microwaves for these type of applications, because largely industrial heating is done by natural gas and burning that gas, which creates a lot of CO2 into the atmosphere. So one, they want to reduce their CO2 footprint. So they're looking at ways that they can electrify these processes. And microwaves can very easily work with the food industry, because there's water in all of the food, and it's very efficient at heating and using that water to perform these processes. The other thing is, you know, electricity is more expensive than natural gas right now. So those microwaves have to have an extra added benefit to entice industry to want to adopt this technology. So while they're cutting their CO2 footprint, that may not be enough to entice them into using a new technology. However, microwaves tend to cut your processing time. So that saves money, because you're not either using more energy to do the same thing, or you can produce more units in the same amount of time that you were doing with a conventional method. It often also gives you added benefits to the product. You get a better product at the end of higher quality. With foods, they maintain the taste better than conventional cooking. And so this has been a successful market that microwaves, you know, has grown in. Next slide. So, you know, the food and agricultural industry, like I said, is a little bit intuitive, right, to use microwaves in, because it's familiar to us. But there are other emerging markets that microwaves are really, you know, coming into their own. And one is that circular economy, taking plastics. There's a company called Pyrowave here in the US that takes polystyrene and can break that down and make new plastics. So polystyrene is not a plastic that is recycled today, right? It is largely thrown away. So wouldn't it be nice if you could have centralized recycling facilities that could take that polystyrene, break it back down, and make new polystyrene plates, you know? And then you have companies like New Ionic, who is looking at that hydrogen production problem. Most of our hydrogen today comes from methane reforming. So we're taking that natural gas, that methane, we're burning it to heat up the reactor to take the methane to make hydrogen. So we're using a lot of natural gas to make hydrogen. So what if we could just even take that first step and electrify that reactor. So we can use microwaves now instead to heat this process. So we're still making hydrogen and we are still using natural gas, but we've reduced the CO2 footprint by at least 30% by offsetting the natural gas that we use to make the heat and replacing it with microwaves. And so these are just two examples of the ways that microwaves are starting to move more into, the chemical sector. Next slide. So at NETL, we work on a number of these processes as well with industry and in universities. So I mentioned that, electrification piece, which is really important. What processes take a lot of energy, need a lot of fuels to create the product, and can we use microwaves to electrify that? So things like ammonia synthesis, hydrogen production that I just talked to, carbon capture, and material processing, things like the steel making industry, which again uses a lot of natural gas to make the iron and steel. You have these new emerging markets, waste to fuels. Can we make gasoline? Can we make other fuels out of plastics and biomass? The plastic circular economy. So there are lots of other plastics like polystyrene that are not currently recycled. Can we take those, break it down into its starting components and make new plastics out of them? And then also critical mineral recovery, which is essential for battery technology, our electronics. Can we use microwaves to get at those critical minerals more easily out of either waste products or ores? And then finally, we're preparing a lot of research tools. So there's a lot of equipment and predictive models that are needed to really advance this technology. And our group has really tried to advance in that space to make this technology more approachable. Next slide. And so when I talk about, our capabilities, I'll just highlight quickly, but we have the React facility, which houses a number of, our specialty made microwaves. So we can do all kinds of different chemical processes, and we can work with industry and match their processing conditions, and test realistic feedstocks and gas flows to know, whether microwaves can work for their process or not. And then we've added a lot of advanced diagnostics and characterization equipment that we've made in-house and worked with other companies and manufacturers to create these one-of-a-kind tools to be used by us and others in academia and industry to try to use this technology more broadly. Next slide. And so while there's a lot of, hope, right, for the microwave, and it's been demonstrated in a lot of different areas, there's still a lot of barriers to really getting this integrated with the chemical industry, for example. So one is, we do lack a lot of those predictive tools, a lot of the simulations that other types of processes, just traditional thermal processes, can use, which cuts down on the cost of developing a new technology. We use simulations all the time to try to narrow down the conditions and parameters that we need before we build something and test something. And in the microwave world, those tools are kind of limited. So we really need to create the computational models and a lot of the data sets that other technologies have. The other is there's still a lot of questions around this new business model of making a lot of small plants versus one big plant. So they want to know, well, what if I really want to make the microwave just as big as I have this other reactor? And so we have to think about, really how big can we make this microwave? What does it look like? What does the economics look like? And how will this affect the rest of the plant? And then lastly is just having more examples in industry, more companies that are using this technology to highlight what we can do with microwaves. Next slide. All right, so that all-important question of workforce development. So we have this new technology, but what's going to be required, right, of those developing and working with this technology in the future? So anytime we're talking about electrification, right, of a process, that's going to require a certain set of skills. And microwaves are no different, right? You're going to need a lot more electricians. You're going to need more in controls development, programming, automation is going to be very important for technologies like these. Programming, right? I mentioned the simulation, the software. You have to code that yourself. You have to develop these tools. We also need more physicists working with chemical engineers and electrical engineers working alongside, process development. And so you start thinking about all of the different types of teams that are going to be working together that probably didn't work together in the past when it comes to making chemicals. And you're seeing an uptick of universities that are really expanding research programs and courses that are being offered for things like microwaves and RF, induction heating, all of these electrified methods that we're seeing coming up in the future. I listed a few, but this is not an exhaustive list, right? And so you have universities that specialize in the chemistry portion of it, the catalyst development that we do here as well. You have hardware development, so that's anywhere from the electrical components, the generators of these microwaves, to the reactors themselves, right? And then you have sensors, very important. You have to know what's happening inside that reactor. You can't put traditional thermocouples in a microwave, so that creates the need for better sensors. And then computational, right? So not only just the physical computational simulations that happen within the reactor, but also on a molecular level. What are the microwaves doing to that material? Next slide. And so here's just a couple of observations that we've seen, over the past 7 or 8 years as we're working with this new technology, and what we feel is a need, right, of really propelling this technology. One is more cross-cutting within engineering programs. There really needs to be a lot more interaction between, chemical engineering and electrical engineering and physics. I don't know that there's a lot of chemical engineers and electrical engineering departments that work a lot together. And for applications like this, we're going to have to see a lot more bridging of those types of fields. And that's, creates teams with different diverse backgrounds. So within my team, we have chemical engineers, we have material scientists, we have electrical engineers, we have people that work more on the biomass and agricultural side of things. We have chemists and physicists. So we have a very diverse team, and we all sit in a room together, and everybody brings a unique point of view to something like applying microwaves to chemistry, right? It's just not the same as heating something up that we've been doing for hundreds of years. And so being able to work with a team is extremely important, right? And I think that can start very early in school. We all had like senior design projects. What if those senior design projects you're required to have someone in each discipline? So you have to have a chemical engineer, a mechanical engineer, a material scientist, an electrical engineer, and a computer engineer all together, right? So learning how to work with unique set of views very early and not being so siloed, I think is very important, not just in microwaves. I think that is very important, an important skill set to have just generally in the workforce. And then there's going to need to be some better understanding of the development pathway of a technology. So when I was, going through school as an engineer, I was very focused on the product I was making, the chemistry I was making. I was only thinking of, what I was doing at that time, right? Creating a material. I wasn't thinking how that material is being used in the plant, right? I'm making a single component. I'm not really thinking of the big picture. And when you start trying to move a technology and develop it and getting it adopted into industry, you really have to have a better understanding of that big picture. So understanding sensitivity analysis around economics, the life cycle analysis, what capabilities are needed to really build out a project. So what people are you going to need in place? What kind of equipment are you going to need in place? And being able to identify pain points within an industry. So we may want to work on a certain chemistry because we think it's really cool. But what if that chemistry isn't, especially of interest to someone that's going to commercialize it? We need to have these discussions with industry and understand what are their needs, what are barriers to them with integrating with renewable, or are there specific chemistries or specific processes that they're worried about electrifying, and coming at it from that approach, other than I have a really good idea for methanol synthesis, right? So I think having a global view of our problems just helps research in general and helps this technology development. Next slide. So that was kind of my brief overview of microwave technologies and kind of where I see the trajectory. Please feel free to ask any questions, and I'm glad to answer any questions you have today.
Great. Thanks, Christina. That was a really good, succinct Energy 101 on microwave energy technology. It's something I would have to admit was kind of intimidating for me. I didn't know much about microwave energy technology, and now I feel like I know at least a good fundamental basis for it. So it's exactly the point of this this format. So I just wanted to maybe open it up with some discussion around. You touched upon some of the workforce implications and some of the things hindering, wide, commercialization of the technology. I feel maybe there's still some technological R&D stuff that needs to go on too, right? So you're using small reactor, or I don't know what you call them, but small reactors. I assume those need to be scaled up for like the example you gave around ammonia production, for example.
Yeah, absolutely. So more pilot scale and commercial scale demonstrations. I think that is very critical for larger industrial adoption. So we work with companies like New Ionic who already have, pilot scale facilities to test out new materials. We work with microwave vendors just, to help with some of the simulations. And we want to partner with industry to start installing some of these, larger reactor designs so that we can show people that this is possible outside of food and agriculture.
There's a question from Ben Gibbons. In solid feedstock settings like waste gasification, is there viability for continuous reactions such as a moving bed system? Would you be able to describe the limitations regarding continuous microwave reactions, if any?
Sure. So yes, there is a lot of viability for continuous reactions. So we do have a large gasification program here, and do have a moving bed set up. And so there are some limitations with microwaves. It's not necessarily in moving the feedstock in and out, that's very doable. The limitation you come into is the actual diameter, right, of the tube, and trying to make sure that your temperature is uniform. And so there is a lot of, modeling that goes into that to make sure that you are applying the microwave in the right spot. But you can use, there are specialty designed auger systems that you can put in a microwave. There's conveyor belt systems, and there's fluidized beds. And so I think an interesting area to really explore is groups that are fantastic at traditional reactor design. And can we take some of those people that are extremely good at reactor design and put them with some RF engineers and figure out, where do we input the microwave? Can we use some more traditional bed designs and integrate the microwave into them? So you can use, metal vessels that contains the microwaves. And so you really just need a port in for the microwaves. And you just have to make sure that you don't have, holes larger than the microwave itself to keep everything contained. So yeah, the continuous feed systems are definitely a high priority for things like gasification and solid feedstocks.
So this next question is from Ansen. He also compliments you on a really nice, informative talk. You did give great Energy 101. NETL also focuses on carbon sequestration technology. So can we expect a technology that will marry microwave technology with carbon sequestration? So in addition to the reduction of carbon footprint, the microwave technology can open the opportunity to explore new reactions that were not done before.
Yeah, so in the carbon capture utilization space, so we do use microwaves for carbon capture, right? You have your either point source, right, where you have CO2 coming out of a stack, and you have a material that's absorbing all that CO2. Typically, to release the CO2 and to be able to store it somewhere, you have to do a temperature swing or a pressure swing. So apply, heat up the material or apply a pressure. And so we can use microwaves to apply that temperature swing, and we can quickly get the CO2 off of the adsorbent and have it stored somewhere. So that's one way that microwaves are being utilized for like the carbon capture side of things. And then instead of like sequestration, we have CO2 utilization. So can we take that captured CO2 and transform it into chemicals? And so we're definitely looking at using microwaves for that chemistry as well.
So I remember, this is a question from my perspective, but I remember like Jiffy Pop that you could do on the stove. So, and you were talking about one of the like industrial large scale utilizations in microwave technology, maybe in food, food consumption or distribution of large scale food stuff. Is there a taste and difference in taste from something that gets like, convectionally cooked versus like microwave? Is that a concern?
Yeah, so from what I understand, I don't work in food science, but I have been told by multiple companies that typically when they're using microwaves for, like, microwaves are used for freeze drying. I know that sounds weird, but you can use microwaves for freeze drying or dehydrating foods, and the foods actually retain their taste better with use of microwaves. It gives a crisper texture a lot of times. And the microwave companies work with these industries, like people, if they've had a product out for a very long time, right, like a cookie, that cookie has a very particular texture, right, and taste. And so they will work with that company to actually match the taste and texture as closely as possible, because if you've been buying like Chips Ahoy, right, you don't want that Chips Ahoy to taste different, right? You want the same Chips Ahoy that you've had since your childhood. And so you can change the processing parameters of the microwave to mimic the things that come out of an oven, or you can upgrade the product.
And so, are you aware of any, or is NETL involved in any large scale pilots around microwave technology and high energy use industries like, ammonia production or, steel or other kind of like high energy use industries? Are there out there? Like any project?
We are working on a number of contracts. Some of them will be publicized very soon.
Okay, great. So this is kind of a way to get us back to like a little bit of the workforce.
Mhm.
Like I would imagine we're going to learn a lot about what different skills or different training is necessary for essentially the same people that are in that plant, but now the energy source is coming from something different. So um, I guess from the presentation, it looks like there's not too much difference so far, at least at the technical workforce level, uh, with someone working in a microwave energy, industry plant versus a, natural gas plant or something. But I could be wrong, and I guess we'll find out.
Yeah, I mean, I think they would probably just have some high voltage training, right? Instead
Yeah.
of having to deal with high heat. With the microwaves, you don't have to have as much insulation around the reactors and things like that. So you don't have as much of that in your, training that you would do as a technician. Instead, it would just be making sure you're aware that things are electrified now.
And so we have one more question, and then we'll open it up a little bit more to the workforce discussion.
Mhm.
And I apologize if I get this name wrong. Kwayun Yen. Thank you, Christina. Question: do you know the best electrical consumption for producing hydrogen via microwave technology? How is that number compared to energy density of hydrogen?
Yeah, so right now we have a methane reforming process that is better than the electrical consumption for electrochemical production of hydrogen. So water splitting, we can beat the electrical consumption using a microwave. And so we're looking to scale that technology up, and it'll be piloted hopefully later this year. I don't have the answer for you on energy density of hydrogen.
Do you know if any of the hydrogen hubs had a microwave energy tilt to them? The ones that were already previously awarded?
I'm not sure.
Okay.
Yeah, so the research side of NETL was not involved with the hydrogen hubs.
Anthony, did you have any questions for Christina while we're
I
here?
think you might have asked it already. My question was going to be related to the workforce development as far as, so she did a really good job of showing potential professional degrees that might be related. And I even showed some universities that are starting to have microwave type programs.
Mhm.
But I was trying to pivot to maybe technical workforce, community college type training.
Mhm.
You mentioned, electrical having high voltage type
Mhm.
training, but I didn't know if there was any other skills that you project
Yeah.
um, could be needed, with the trades and community colleges.
Yeah, of course. I mean, automations and controls, right? Programming is always a good thing to have, because with these, the microwaves are going to be automated, right? And it's much like machining has become automated, right? These 5-axis, 6-axis mills are all a code now. And being able to understand that code and being able to go in and modify and make it more efficient is an important skill to have. And the same will be true for a lot of these, electrification methods.
Yeah. Thank you.
Mhm.
We have another question from Ayaka Jones on megawatt microwave uh, use in carbon capture, regeneration of solvents. Could you comment on the pros and cons of using microwaves versus using traditional exchangers?
Mhm.
Well, we've
Sure.
got a lot of people with a lot of microwave knowledge. So,
Yeah, that's good. So for regeneration, you're mainly looking at the time to get to temperature is much quicker. So your regeneration time is cut by half compared to some traditional heat exchangers or traditional heating methods. So again, when you're just interacting with the material itself and not the vessel walls, you can quickly get to temperature, release the CO2, and then when you turn the microwaves off, everything also cools a lot more quickly because you haven't brought the walls up to temperature as well. And so just your recycle times can happen a lot faster. The cons are we don't fully understand how far we can go with those recycle times, how many cycles can, at least solid materials. Liquid materials are a little easier to understand the lifetime, but solid sorbents, we're still trying to figure out what is the cap. Are we doing any detrimental changes to the material by rapidly cycling up and down? And so that would be a current con to the technology.
Okay, so I think we're probably going to wrap it up here. I think we got to everybody's questions. But Anthony, do you have any more updates or anything you'd like to mention about the Regional Workforce Initiative and what we're doing next year, or
I will say this, Matt. Yeah, I'll say this. We're hoping to have one more webinar this calendar year. If we do, I'm trying to lock in the presenter for early to mid-December, and that would be the briefing on the U.S. Energy and Employment Report. So hopefully we have an announcement here shortly, coming days or week, that'll announce that one. But just trying to coordinate with the potential speaker on that.
Well, I'll close it out now by saying it was really interesting to hear about new technology to me, and I'm sure to a lot of other people on the webinar. And it was extremely informative and a perfect energy 101, I think.
I agree.
So thank you for your time, and thank you everybody for your time, but thank you for the presenters for your time. And we'll see you soon, hopefully. Have a great afternoon.
Thanks, everyone. Thanks, Christina. Have a great day, everyone.
Bye. Thank you.